section 4.4, we're going to do operations and different bases. So we're going to add bases that are other than 10. We're going to subtract, multiply, and divide, and do the arithmetic with those bases. For the most part, algebraic operations can be performed in other base number systems just like they're performed in base 10. So for example, 4 plus 3 and base 5 is 12, and then everyone stopped and just said, what? Why is for the same reason that 9 plus 3 is 12 and base 10. When adding 3 and 9, I have to get the highest digit in base 10, which is 9. So we have to wrap around to get 1 0 with 2 ones left over. So in other words, 4 base 5 plus 3 base 5 is going to be 12 because I have to remember I'm in base 5. So when working in a different base, you could build an addition table that would help you by taking all the numbers, writing them out, and 0 plus 0 is 0. 1 plus 0 is 1. And so this works out pretty nicely. As you get into the information here, though, I see 2 plus 4 exceeds my base, which is why I start saying, well, it has 1, remainder of 1, 1, remainder of 2, 1, remainder of 3. So you have to stop thinking about this as 11 and 12. You have to start thinking about, if I'm in base 5, this is actually 5 and 0, which would be 4 plus 1 in base 10. If I do 4 plus 2, that's going to be 1 5 with 1 remainder. So it's going to be a little tricky there. So in order to add using the table, you have to generate the table first, and then you have to be used to the idea of carrying digits or having those remainders listed and recognizing that a 2-digit number does not mean the same thing as it does in base 10. So let's look at an example. If I want to add 324 plus 24 all in base 5, I'm going to add the digits in one column. So if I have 4 plus 4, that's going to be 8, which when I look at 8, that is 1 5 with a remainder of 3. So I put my remainder underneath and I have to carry that 1 5. Then I have 2 plus 2 is 4, plus 1 is 5. And so when I do that, that's 5. 5 is 0, carry the 1 because it's a whole 5. 3 plus 1 is 4, so that's how we get 403 in base 5. Let's look at this example. 1244 base 5 plus 333. Well, 4 plus 3 is 7, which would be 5 with a remainder of 2. So when I'm talking about a 5, that means it's 5's place, so I have 1 5's place. 4 plus 3 is 7, plus 1 is 8. 8 is 5 remainder 3. So I put the 3, carry that whole number 5 to the top. 2 plus 3 is 5, plus 1 is 6. 6 is 1 5 with a remainder of 1. And 1 plus 1 is 2. So that's how I'm generating those sums there. So really take your time, and you have to start thinking about 6 is 5 remainder 1. 7 is 5 remainder 2. That's what helps us do our arithmetic. If I wanted to use the table solution, this is what I would have to do. In this case, I don't think the table solution is often as helpful as some people think that it is. In the hexadecimal system, I have letters as well as numbers, and that adds a whole nother layer of complication to it. So I have 135E 16, 217, 16. So if I have E and C, that gives me A. That's wild, right? So if I look at E and C and I see what those are related to numerically, then that's going to help me out with the hexadecimal system. And so I'm going to land at 157 remainder A. Now subtraction in other bases is going to be very similar. If I have 12 base 4 minus 4, 12 base 5 minus 4 base 5, I need to think of that as 12 minus 4, and base 10 would be different. So I would look at that table, identify the 12, and that's going to be 4 and 3. So that is going to be 3 base 5. So here's another example. This is what speaks more to me, is actually lining them up. I can't do 1 minus 3 when I have them written up. So I need to actually make that 1 into a 5. So I can take a 5 from the 2 and bring it over and have 2 1s, and then I can do that and do the subtraction of 3, and then I have nothing, nothing, because I've borrowed over borrowed. So in step 1, since 3 is larger, I do have to borrow 1. And 1 minus 3 still doesn't work. So I changed 2 into the 5's column to a 1, and a 1 in the 1's column into an 11. So that's why. So I have 11 minus 3. This makes it 11 minus 3, which is going to be 3 base 5. Then in the second column, I have 1 base 5 minus 2 base 5. I need that 1 to be larger. I'm going to borrow, and so that gives me 11. 11 minus 2 base 5 is going to be 4 base 5. And then same thing in step 3, 2 minus 1 base 5 is 1 base 5. So the difference would be 143. If I want to multiply in base 5, I can use a multiplication table. So 2 times 2 is 4, 3 times 2, and so because I'm in base 5, you have to remember this is not 11, this is really 6, which is 1 5, 1 1. So when I'm utilizing that table, it can be somewhat easier to do the multiplication, or we can write them vertically and start working together. So 4 times 3 is 12, but I'm wanting it to be in base 5. So that is 2 5s with a remainder of 2, because 2 times 5 is 10. So I carry my 2 5s up, and then I have 2 times 2, which is 4. Sorry. 2 times 1, which is 2, plus 2 is 4. So that's going to give me 0, because 4 is not divisible by 5. And then I'm going to carry the 1. And then I have 3 times what's here plus 1. And I get 2 with a remainder of 0. So I get 2002 base 5. All right, so I can add my partial products because I have a 2-digit number, just like I do in base 10, and that does give me a final answer. In part B, it's a little bit easier to do a binary multiplication because 1 times 1 is 1, 1 times 1 is 1. Then I have 1 times 0, 1 times 1. So binary is going to be a lot easier to do this, and then you have to do the second digit, 1 times 1, 1 times 1, 1 times 0. 1 times 1, remembering to add that 0 in just like you do in base 10. If I want to divide in base 5, this can also be a little tricky. So if I want to do 3 base 5 divided into 2032 base 5, I can use the multiplication table to be able to function in the division. Or I can do a long division problem where I realize that 3 base 5 can't go into 2 base 5. So then I'm going to have to look at it as a whole. I'm sorry, 3 can't go into 2. Yeah. And so I have to bring 3 into 20. And so when I bring 3 into 20 and base 5, that is where I'm going to get the 14 from. And I'm going to carry the 3 down just like I do in my traditional math. And then I have a remainder of 11 because that's twice, with the remainder of 11 here, and so I'm going to work together with that, and I bring the 2 down, and I get a 22, because I'm carrying that 2 down to the bottom. From that 22, I can say, well, 3 base 5 goes into 22, and then I'm able to say, well, that's going to be a 0. Whoops. And then I'm able to write the 4 in the quotient and the 22 below, subtract them, the remainder is 0. So this gives us 324 base 5 with no remainders. I can also check this by multiplying out the standard form. But arithmetic and other bases, if you find this overly complex, convert everything to base 10 and then convert your answer back to base 5. So that's my recommendation, is if this really isn't clicking, doing it in that base, work with it that way and do it, convert everything to base 10, do the arithmetic, and then convert it back into the base that you want.